As you saw above, the general antiderivative can result in several different functions. In fact, an infinite number of functions, since c can be any constant. And so in this video, we're going to be looking at what happens when we're given an initial value, how we can solve for the specific antiderivative. So I'm going to look at two examples. The first example gives us a function f of x equals sine of x. And they first ask us to find the general antiderivative, and then we're going to use an initial condition to find the specific antiderivative. Okay, so the general antiderivative, which we will call f of x, capital F of x, is equal to the integral of sine of x dx, or the antiderivative of sine of x dx. And we can just use our formula that we learned above, and the integral of sine of x is just negative cosine x, and we put plus c. Okay, so now they're going to give us an initial condition, and the initial condition they give us is that f of 0 equals 5. So we know if we plug 0 in for x, we're going to get 5. So I'm going to do just that. Negative cosine of 0 plus c is going to equal 5. And then all we need to do is solve for c. So we get 5 equals, cosine of 0 is just negative, cosine of 0 is just 1, so this would be negative 1 plus c. So then I can add 1 to both sides, and I get c equals 6. So that is my specific antiderivative. So this is going to be negative cosine of x plus 6. That is my answer. In the second problem, I'm asked to solve the initial value problem dy over dx equals x squared minus 1 and y of 3 equals 7. So notice the notation here is a bit different, but I want you to become familiar with a couple of different notations. So they're asking us to solve the initial value problem, which should trigger you to think that this is an antiderivative. And so to find y, I'm going to simply take the antiderivative. And the antiderivative looks like this, x squared minus 1 dx. And remember, our sum and difference rule means that we can split this up. So y is equal to the integral of x squared dx minus the integral of 1 dx. Now we can just use our formulas, and we know that the integral of x squared is just going to be x to the 2 plus 1. We're going to add 1 to the exponent, and then we're going to divide by that same thing, right? And then if you want, you can put a plus c sub 1 to represent the antiderivative of the first section. And then we're going to take the antiderivative of the second section. So we have minus. The antiderivative of 1 is just going to be x. And then we can put a plus c2 if we want. Now we can combine those two constants to make one large constant, right? So we have x cubed over 3. You can also write that as 1/3 x cubed minus x plus c. And so now we have our general antiderivative. That's our general antiderivative. We know, though, that the initial condition when x is 3, y is 7. So I can plug 3 in for x and 7 in for y. And so I get 3 cubed over 3 minus 3 plus c. So that gives me 7 equals, one of my 3's is going to cancel, so I'm going to just have a 3 squared in this first term. So that's going to be 9 minus 3 plus c. So now I have 7 equals 6 plus c, and therefore c equals 1. So my specific antiderivative in this case, which we were able to solve for because we had an initial value, is going to be y equals 1/3 or 1/3 x cubed, or you can write that as x cubed over 3 minus x plus 1. And with these antiderivative problems or initial value problems, you can always check your answers by taking the derivative, and you should get back to the original problem that you were given.